Please welcome to the solution video of the puzzle Wheel in Motion, an advanced puzzle from June 7th, 2024, and it features two squares sharing a vertex and a circle, and on that circle are three other vertices, and the center of the circle is also a vertex of the smaller green square. And we are asked to find this angle, and as you can see it must be 90 degrees. Yes, it looks like it's 90 degrees, so we're asked to prove that this is 90 degrees, and I'm gonna use vectors for that proof. First of all, I'm gonna choose the origin. I'll choose it in the center of the circle. That's the origin. Here I say we have the endpoint of vector A, and here we have the endpoint of vector B. And then I'm going to say a rotation, a clockwise rotation over 90 degrees will end up, of vector A will end up here. So if I say R is that rotation, RA, the clockwise rotation over 90 degrees ends up there. So there we have vector RA. The sum of those two will end up over here, so we have here R plus RA. Now, the vector which is along this side of the red square is the difference of those two vectors, so we have there A plus RE, A plus RE, A plus RA minus B. That's the vector from there to there. Then I'm going to say again, I'm going to apply on that vector a rotation over 90 degrees, so that R, we'll get here the vector RA plus R squared, so 2 times applied, minus RB. Yeah, so that's the other side of the large square from there to there. And I'm going to simplify that a bit, because I know that 2 rotations over 90 degrees is a rotation over 180 degrees, which is minus the identity. So I'm gonna, that middle term, I'm going to say that this is RA minus A minus RB. Yeah, by using the fact that R squared is minus 1. So what's then this vector from the origin to there? Well, that's basically B plus that side. So over there we get B plus RA minus A minus RB. Yeah, so that's that vector. Okay, now I'm gonna, okay, there's one more vector that's from there to there, so we get B minus RA for this one, B minus RA for that line segment over there. So from there to there, and I'm gonna take the dot product of those two vectors, so this vector and that vector, and I'm gonna take their dot product and see what it evaluates to. So the dot product of B, the dot product of B minus RA, and I'm gonna, that's the dot product, it's an asterisk, and to B plus RA minus A minus RB. What is that? B minus RA, yes. I'm gonna rewrite this, first I'm gonna take B minus RA and then the dot product with B plus RA and minus B minus RA and the dot product of A plus RB. That's just basic factoring out. Well, the first term, it's very easy to see that this is B dot product B minus RA dot product RA. And the second term, I'm gonna factor out one rotation of the second term, so this is minus B minus RA, and then times the rotation of B minus RA. And I'll have to explain what I've just did. If I take out the R from here, of course, then by the B you get this. And I've used again that A is minus R squared of A, and I'm taking out one of those R. So here, if you say R times R, that's minus 1. So you'll see that this is basically the same. Okay, now we have two terms. Well, the B dot B I'll leave as it is, and I'll see that I have RA with the dot product with itself, and I know that the dot product is invariant under rotation. So this is basically the same as A dot product of A. So because what I just said, rotation leaves invariant the dot product. Then the other term, what I see is that I have a vector B minus RA and the dot product with its rotation. Again, we have here B minus RA. So a vector and the dot product with its rotation, well, you know, it's 90 degrees rotation, so that's 0. The dot product of an orthogonal vectors is 0. So that term cancels out completely. So what we have found is that this evaluates to B times B minus A times A. And because both are on a circle, they have the same length. So basically this is the square of the length of B and this is the square of the length of A. And since they have equal length, we know that this must be 0. So what we have found is that the dot product of those two vectors is 0, and that implies that they are orthogonal. In other words, the angle alpha is 90 degrees. And that completes the proof of the puzzle Wheel in Motion.